Okay, this lecture brings us to a very exciting part of this course, namely statistical inference. Everything that we've done so far, we did in preparation for statistical inference. So we looked at basic probability, we looked at probability distributions, discrete and continuous, we looked at special distributions, and then we also looked at sampling distributions. Now we are going to use all this knowledge to help us with statistical inference. Now, statistical inference is the process by which we use the information from a sample to draw conclusions regarding the population. Statistical inference has two main categories, namely estimation and hypothesis testing. We are going to concentrate on estimation for the next few lectures. With estimation, we use a sample statistic, like the sample mean, so that's a measure that we calculate from sample data, to estimate the population parameter, like the population mean. So the population parameter is unknown, and we use a sample statistic to estimate this population parameter. The sample mean, capital X bar, is called the estimator of the population mean mu. So the estimator is a rule or a function for calculating an estimate. An estimate, on the other side, is the result of this function if we substitute sample values into this function. And an estimate is then usually indicated by a lowercase letter. Let's look at this example. A car manufacturer wants to estimate the average fuel consumption in liters per kilometer of a specific model car. The manufacturer takes a random sample of 10 cars of this model and subjects them to a road test of 500 kilometers. And the sample mean is then 5.78 liters per kilometer. Suppose that the manufacturer used a sample of 100 cars and calculated a sample mean of 5.9 liters per kilometer. So here we have two estimates of the unknown population mean, the unknown average fuel consumption. Which one of these two estimates would you prefer? I think that most of you will agree that we will use the estimate calculated from a sample of size 100. Why would we rather go with the 5.9 liters per kilometer? Because it was calculated from a bigger sample, and a bigger sample contains more information, and therefore we expect it to be a better estimate of the unknown population mean. Now, a point estimate is something like what we have in this example, where we use a single numerical value to estimate the unknown population parameter. The problem with a point estimate is that it does not reflect the effect of the sample size. On the other hand, we have an interval estimate or a confidence interval. And this is a set of consecutive values that is used to estimate an unknown population parameter with a specified degree of certainty. For example, the car manufacturer can now, instead of a point estimate, make use of an interval in which the unknown population parameter is expected to fall. In this table, we have some population parameters as well as their estimators. For example, the population mean mu is estimated by the sample mean X bar. The population variance sigma squared is estimated by the sample variance S squared. And the population proportion P is estimated by the sample proportion P hat, which is X over N. X is the number of successes over N, the sample size. So why do we choose these estimators to estimate these unknown population parameters? Of course, it sounds just logical to use the sample mean to estimate the population mean and so forth, but there are objective measures to determine whether an estimator is a good estimator. And we will now look at 3 of those measures. First of all, an unbiased estimator. An unbiased estimator of a population parameter is an estimator whose expected value is equal to the parameter. If you think back to the sampling distribution of the sample mean, you will remember that the expected value of the sample mean, or the mean of the sample mean, is equal to the population mean mu. Now the next question we would like to ask is, how close can we expect this estimator to be to the parameter? And that brings us to consistency. An unbiased estimator is consistent if the difference between the estimator and the parameter decreases when the sample size increases. Now again, if you think back to sampling distributions, we will use the standard deviation of our estimate, which we called the standard error, as a measure of closeness. We know that the standard error of the sample mean is given by sigma over square root n. So sigma is the population standard deviation over the square root of the sample size. So that means that the standard deviation of the sample mean becomes smaller and smaller as my sample size n increases, because I divide by the square root of n. On this slide, both the properties of unbiasedness and consistency are illustrated. Suppose that we would like to estimate the population mean mu, which in this case is 5.86. And we use the sample mean x bar to estimate the population mean. Now, in the red graph, we have the sampling distribution of x bar when we work with a sample of size 10. And in the blue graph, we have the sampling distribution of x bar when we work with a sample of size 100. And we can see that the expected value of x bar in both these cases are equal to the unknown population mean mu. And therefore we can say that x bar is an unbiased estimator. Okay, we can also see that the variation for the blue graph is smaller than the variation for the red graph. And this is an illustration of the property of consistency. When the sample size becomes larger, the standard error or the variation in our sampling distribution becomes smaller. And that is a property that we also want for an estimator, that when my sample size increases, then my standard error or the variation in my sampling distribution must decrease. And we want the standard error to be small, because that's an indication of how far we expect the estimate to lie from the unknown parameter. So for the blue one, we expect that the sample mean will lie close to the unknown parameter, whereas for the red one, the sample mean can lie also far from the population parameter. And then lastly, efficiency. If we have two unbiased estimators of a parameter, the one with the smallest standard deviation for a given n is called an efficient estimator. For example, if we sample from a normal population, both the sample mean x bar and the sample median are unbiased estimators for the population mean. So the expected value of the sample mean and the expected value of the median will give me the mean of the population. However, the variance for the sample mean, which we now know is sigma squared over n, is smaller than the variance for the sample median. The variance for the sample median is given by 1.57 sigma squared over n, and therefore we will prefer the sample mean as an estimator to the median as an estimator, because it has a smaller variance.